You ready? No. Okay, our last speaker of this session is Taro, who's going to be talking about algebraic temporal effects.
Okay, thank you. So this is a joint work with Hiroshi at Tohoku University. So in this talk, we are studying temporal verification, especially linear time temporal verifications. The aim of the linear time temporal verification is to verify the traces generated by the program. So in this case, the trace means that some sequence of the effect or event triggered by the programs, and it may be infinite, right? And there are two major classes for temporal verification properties, and one is safety properties, which means that no trace reaches to an undesired state. So another class is liveness properties, which states that any trace can be extended to a desired trace in the future. Okay, and there are many applications of the temporal verification, including resource usage analysis, access control, availability, and so on. Okay, so let me show one simple example. Here it defines a recursive function f, and it takes file names and just opens the file, reads the contents, and close the file, and then the function is called recursively. So if we are interested in the use of the file manipulation operations, then here the trace generated trace consists of the three effects: open, read, close. And in this case, by calling this recursive function, the infinite trace like this one is generated. Here open, it just consists of the infinite repetitions of the open, read, close, and so on. Right. And for the one example of safety properties for file manipulation is that the file should be the read and close only after opened. So such properties can be checked by verifying that some undesired trace is not generated. And the examples of the liveness property is that the file will be closed eventually after opened. So such properties can be checked by verifying that some desired trace should be generated after opened. Right. So in our work, we are focused on temporal effect systems, which is a type and effect system for linear time temporal verifications. And yes, and the temporal effect systems have some benefit types oriented by the type systems, like the higher support for higher order functions, type-based abstractions, compositional verifications, and so on. And the temporal effect systems have been studied so far for some programming features, like the recursive functions and faster class continuations. But the current temporal effect systems have some limitations. So the first limitation is that the temporal effect systems are specialized in only in recursive functions. So then it is unclear how we can address the more general recursive structures. The second limitation is that the existing temporal effect systems are specialized in some specific form of a temporal effect. So like in some work, the temporal effects are described using fixpoint logical formulas or automata. But if we want to use another representations, one needs to redo the proving work, like proving the soundness theorems. So of course, it is not a desired situation. So the open question is that how we can abstract these different effect representations to a more uniform or abstract representations. All right, so we answer these. In this work, we answered these questions. For the first question, we extended the temporal effect system to recursive types. So as you know, recursive types are very expressive and general programming features. So by extending with recursive types, we can implement many programming features and paradigms, like the object-oriented programs, cooperative schedulers, and recursive structures. Right. And but the challenge in this extension is that the reasoning about the infinite behavior becomes much harder. So it looks like the infinite liveness properties. So because the use of the recursive types includes some more complex recursive structure, so it is a very challenging problem. And we solved this challenge by using guarded recursive types with a later modality. Right, and for the second questions, we introduced a more abstract form of a temporal effect. And actually, it is just provide only algebraic structure of a temporal effect. And we also assume that some operations are necessary to, for sound reasoning in temporal verifications. And we also provide some two instances of this algebraic abstractions. One is based on omega regular expressions, and one is based on fixed point logical formulas. All right, this is a summary of our work. So let me explain the more details of our work now. So first, I will start with a background of the temporal effect system. So the temporal effect system provides some special form of effect called the temporal effect. But the temporal effect is just a pair of finite effect and infinite effect. And the finite effect represents some a set of finite traces, like the regular expressions. And the infinite effect represents a set of infinite traces, like the omega regular expressions. And the soundness of a temporal effect system means that assigned temporal effect over-approximates the actual behavior of a program. So if the program generates some finite trace, then the generated finite trace should be included in the interpretations of the finite effect. And if the program generates some infinite trace, then it should be included in the infinite effect, right? And yes, so for the examples I presented in this talk, this example satisfies this temporal effect. So it means that this recursive functions satisfies safety and liveness property for files. But if we insert some non-terminating computation before closing the file, this liveness property is broken. So because opened file is not closed. So then temporal effect can reject these examples by soundness. All right. So, but a challenge arising in giving a temporal effect system is in reasoning about the infinite behavior. So infinite behavior is, in general, infinite behavior is defined co-inductively. So here I use the functions, new operations, which means that which returns the greatest fixed point of some monotonic function f, right? And using this greatest fixed new operations, we can, for example, define the non-termination behavior of the programs, like this one. And the problem is that how we can check infinite effects over-approximate the infinite behavior. So this is necessary for soundness of the temporal effect. But yeah, and in other words, so infinite effect iota should be an upper bound of the actual behavior defined by new f. But the problem is that new f is defined using the co-induction, but the co-induction principle is not useful in this case because it only allows under approximation. So, but we want to show that is an over approximation. So co-induction principle cannot be used in this case. So the solution in the existing temporal effect system is to take the greatest fixed point as an infinite effect. So in this case, especially greatest fixed point of the q, and here q is the upper bound of the function f, which defines infinite behavior. Then it is easy to show that the infinite effect nu q is an upper bound of the actual infinite behavior described by the nu f. But the price of this approach is that now infinite effects are no longer invariant. So for example, in the usual type system, so the typing rule for recursive functions can be assigned by assuming that the return type, the function type is invariant of the computations. But now we cannot use this standard typing rule for temporal effect reasoning. And actually, the previous work provides some special typing rule for reasoning about the recursive functions. So in that sense, we need to take a special extreme care of reasoning about the recursive structures. And but one of the issues in the previous work is that the existing temporal effect system only supports only a restricted form of a recursive function. So it is unclear how we can determine the infinite effect for the more general recursive structures, like the recursive types. Yeah, and the second issue is that the representations of the infinite effect relies on some specific operations, like the omega operation in omega regular expressions or new operation in fixed point logic. So it is an open question how we can choose a suitable representation depending on the situation of the user. And to solve these issues, first we introduced the guarded or recursive types with the later modalities, and we use these recursive types to extend the temporal effect systems. And recursive types is just a very standard form. It's just it provides some standard operations of fold, unfold, and fold. And the later types means that intuitively it means that there are some later computations in a sense. And the next constructor means that its argument M is a later computations. And it also provides some operation like add to apply to manipulate some later computations. But I don't go into the detail in this talk. And furthermore, what we support guarded or recursive types means that the type variables bounded by the recursive types is guarded, which means that type variable alpha can appear only under the type constructor, later type constructor. So under these assumptions, the later types and the later computation means that unfolded computation in a sense, in the terminology of the recursive types. So for example, the stream-like types can be given, like the above type here. But can I use those? Yeah, but the below type is not valid types because the occurrence of the type variable is not guarded here. And for the fixed point or combinator, the recursive part, recursive call part, recursive argument part should be guarded here because it corresponds to some later or unfolded computations in the context of the guarded recursive types. All right, and we utilize these guarded or recursive types for sound reasoning in temporal effect systems. So the key observations in guarded recursion is that first, generated infinite trace is split into infinitely many finite traces. And these finite traces happen between the successive some unfolded computations. Or in other words, it happens between the successive next guarded computations. So let me explain more details using these examples. So now I assume that the program M is well typed and it generates some infinite trace. And first, such programs can be evaluated to the term like this one. Here, E1 is just an evaluation context, but the argument of M is the non-terminating term. So this M1. So next, the evaluation go to the evaluation of the M1. And again, the evaluation of M1 reaches to the similar form like this one. So here, argument M2 of next constructor is also non-terminating. And by this under divergence behavior, infinite behavior over programs in guarded recursion, this process is repeated. So then we use this. So then we can use some infinite behavior. We can structure infinite behavior using guarded recursion types. And Next, I explained how we can utilize this phenomenon, general phenomenon for sound reasoning. First, our idea is that first we infer some upper bound of phi of the generated finite traces. And then we can view this infinite computation is more abstract, like this one here. So first, M generates some finite trace W1, but the remaining computation just repeat some generation of some finite trace in phi. Okay. Then we can take the infinite repetitions of the upper bound phi as an infinite effect. Then we can ensure that the originally generated infinite trace is contained in the infinite effect nu q here. And the remaining problem is that how we can infer the upper bound of the finite traces. And for that, we introduced some temporal effect forms augmented with some special operations. And and this is algebraic formulations of our temporal effect. But in this case, in these representations, the algebraic effect is just a pair over finite and infinite effect, and with some additional structures. But the first four structures are fairly standard ones to model the sequential effect with sub-effecting. So I will skip this one. The special operations are last two operations. The rate operations is effect level operations for rate modalities. And the role of the rate operation is to accumulate finite traces generated by the non-terminating programs. And we can achieve this accumulation by introducing this typing rule, and where the rate operations is applied to the infinite effect of the guarded term M. And then we can ensure that if the program, well-typed program, generates some infinite trace, then the trace is split into the infinitely many traces. And the assigned infinite effect can recognize the traces and where the next guarded happens. Finally, we assume some operation fine, which it returns some which assumes that returns the upper bound of the accumulated finite traces. Then we can we can do the sound raising under these assumptions. Yeah, and our soundness theorem is just a summary of what I explained in this talk. Yeah. Okay, so we also discussed some examples and instances of this algebraic temporal effect. But right. Yeah, thank you so much.
Yeah, right here.
Thank you for the mic. There are two ways to compute fixed point of traces, infinite traces. You take all of them, you eliminate the one that don't work. And the other way, you take prefixes and you pass to the limit. You use a second.
Yeah.
And then you have a problem that what is true of all prefixes might not be true of the limit. Mm-hmm. And so why is your type system guaranteeing that the fact that all effects were proved correct for finite execution, why is it still valid when you pass to the limit? You must have something somewhere that I did not see.
I see, yeah. So maybe, okay, so I'm not sure I can answer your question well, but maybe one observation is that first, infinite behavior happens when the infinite behavior happens, the infinite next guarded, okay. So we need to dive into the infinitely many next argument. So in this case, M is first evaluated to the next M1, and next M1 is evaluated. And the evaluation of M1 is evaluated to the next M2, and then M2 is evaluated, and so on. Then, by assuming that the later operation is applied to the next infinite effect of the next argument M, then if this program is diverges, every informations about the infinite behavior must be accumulated.
Mm-hmm. It's true for all iterators, not at the limit. So why do you cannot say express that you are infinitely you must have a restriction on the type.
I see. Right. Yeah, sorry. And then, yes, and actually, we assume that there are some finite effect, there is some finite effect that accommodate all the finite actual traces. Yeah. Right. So we assume that some limit exists in a sense.
Okay, we're at the end of the session, so let's thank Taro and take our next questions to the coffee break.